My name is Joseph Wunderlich. I'm Professor of Engineering, Architecture, and Computer Science. This is a review of a custom lab manual that we've made here at Elizabethtown College. I've been doing this for 24 years here now. We did a similar thing at Purdue, although I had a full-time lab tech that would make these at Purdue when I was a professor there. Now we do it ourselves. So this is my website, Architecture, Computer Engineering. I'm 61 years old, done a bunch of things in my life. So we have computer engineering here, and you'll see all the lab manuals we make down below here. We are in a specific course here, but instead of going into the syllabus, I'm just going to make a generic video for this. We may use this lab manual in other classes too. So you see we have circuit trainers. We do things in mostly TTL 5 volts on our circuit trainer and breadboarding, TTL chips of combination sequential circuit design. We also have microcontroller 8050-251 circuit simulator that we do. We've had a variety of boards in the past, a number of relays. Phoenix Contact is our main partner here for I don't know, several $100,000 worth of parts they've given us over the past 15 years. You'll see different kinds of PLC tutorials for that. And then FPGAs, we have a whole variety of those, both in hardware descriptive language and otherwise, including the original Xilinx compatible IDE development environment. And then Raspberry Pis and ARM microcontrollers and Arduinos and other things like that. We'll have a little manual for that. We're not going to talk about that today. So I'm talking about this right now. The students have this in their hand. And this is for the circuit trainer power supply and the most recent version here. So ICs, integrated circuit chips. These are actually chip packages, right? The chip itself is a piece of silicon off of a wafer that's in here and then soldered to the output buffers. Input buffers are to metal pins of a much larger scale, hundreds of times larger in size. And then that's what interacts with the physical world, but the actual chip itself is a tiny thing. And so this is, these are our Texas Instrument TTL numbers. You can find these by going to a number of places, DigiKey or Mouser, or TTL spec books have hard copies here, a number of places. And so you have OR, this is an OR chip and a 3-input OR, and the pins, notice that you have to power it up. These are active devices. You got to power it up to power and ground, not just the logic inputs and outputs, but these need to be powered. There's a 4-input OR gate, NOR gates. So OR was at 2-input ANDs, 4-input ANDs. We have most of these NAND gates, mostly for VLSI implementations. You go to NANDs. You can do it in here too if you just want all one gate for everything. You can translate everything, including your inverter, to NANDs. Just tying inputs together would be a NAND. Would be an inverter. Tie the inputs of a NAND together would be an inverter. So these are NANDs, quad input NANDs, exclusive ORs, inverters, buffer drivers. So these don't have any logic to do, but they provide isolation like relays when you're connecting things to a bus. We have sometimes do projects in the courses where they have a number of different devices connected to a serial bus, and you have to allow only one thing at a time connected to the bus, one transmitter, one receiver. You can't have everything talking all the time, so you just completely cut off devices with a buffer driver. There's no logic other than just cut off. And so what's this one here? Bus drivers, flip-flops. Now, we haven't done this in this class yet, but these are memory devices, and the students will learn all about this. We'll analyze JK, SR, D, and T flip-flops in the memory devices, and they change in time. So there's a clock on DRAMs. These are the excitation tables. The students will learn about this. They have a lab coming up, intro lab, so they haven't learned this yet, but these are how these devices behave, and you use those to design finite state machines. And then some basic transistor knowledge here. This is more just for reference from other courses. We won't go into the details of that. So just molecules versus atoms versus electrons in the valence shells, and how bonds are made, and the periodic tables and conductors and semiconductors, and doping of semiconductors and why they work. I won't quiz students in this class. It's more for other students. I might, well, I'll just include it in this, what I'm doing right here. So doping of a semiconductor, you get a material with a valence shell such that it wants to either give up the valence shell, each of the shells want to have a certain number of electrons in them. And so if you have, just like in the valence where you need an electron, then it will try to get grabbed. So the semiconductor is nice because it can, depending on the doping of other atoms you put in there, either grab an electron or well, the dopant atom actually makes the acceptor. So they bond nicely to silicon because of the way the valence shell is, where it's got almost complete shell. And so you put an atom in that either wants to give up an electron, a dopant atom, or wants to, and that's called a donor, or one that's an acceptor. And then you make a junction between these two materials, N and P type material, make either a diode or a transistor, NPN material. And the junction characteristics is such that if you have a donor material, a molecule of silicon doped with a donor next to a molecule of silicon doped with an acceptor, you will create the propensity for current to flow, and then it very easily gets tweaked to act as a transistor. And then it's in a lattice structure. Most solids will be in some kind of lattice structure to memorize that. And then how transistors behave. So now, not everybody in this class has had electronics, and you don't need to have had analog circuits to be in this class. But this is the basics of the two different kinds of transistors and how they work with that PN junctions of dopants and donors and acceptors, and how that works. And there's basically two kinds of transistors. And this first kind is a field effect here, where you have these two materials doped in a bigger base that's both doped the opposite. And so you have the propensity for conduction here and here. And the way the catalyst for that is you put on the gate a voltage, which creates a potential, and then a magnetic field that creates a conducting channel, and then things flow. This is nice because there's isolation. There's no current flowing between the gate and drain and gate and source. It's just a voltage creating a magnetic field that makes a conducting channel. So this is nice for low power consumption and higher density. There's a number of properties for CMOS that are nice. And that's really what people do mostly. This now is a binary junction transistor functionality. It's a little different. You put a small amount of current here and it makes a big amount of current here. This is how you make amplifiers. And the downside is there's currents flowing all over the place, and you have to resolve that with your circuit analysis. The upside is you can source, you can amplify, you can also absorb high amounts of static electricity. You also can source a lot of current. These are good for power kind of things. So you do have power FETs, but bipolar is, for what I just said, the MOSFETs typically is what you want to use for digital logic. And then the logic gates. And so the students have already learned these different gates. Well, actually, they haven't looked at the circuits. They don't have to memorize this, but this is what the circuit layout would look like with transistors with an NMOS and PMOS to make an inverter. This is NMOS versus PMOS is the symbols for that. So this is how you put a bunch of transistors together to make these different circuits. And then have those. This is just an example here of CMOS versus bipolar transistor circuits. So this was a neural network chip I made in 1992 in a 5-volt frame. And then the chip pinouts and CMOS FETs in the, or the chip pinout circuits can be either special CMOS FETs, field effect transistors, or the binary junction transistor. We're not going to get into all that here. So I didn't design the frame here, but everything in the middle I designed and built and tested with 10,000 transistors. It's a neural network chip. It was one of two I designed in the early 90s. But anyway, so here, these are some more characteristics of TTL things. So now the teams here will have, in this particular class, and I guess classes in the future too, when they listen, ideally a group that has people with diverse backgrounds. And so it's good if you have somebody who's maybe a pure programmer versus somebody who's a real circuit person. That's good. Or if you're a mix of both, that's fine. But the teams are best, I think, my opinion, if you have people with different skills, because then you complement each other. Now, if you're exactly the same, then maybe you don't argue as much because you just do all, but then you may be missing things because there could be somebody out there that could help shore up things that you're not strong in. Everybody's not strong in everything. Now, this is our circuit trainer here. And so the students will be using this in the next lab. Well, I don't know. When I'm filming this, this is the next lab. It could be different later. And so I want them to analyze the all this. Again, the analog circuit people, engineers will have more familiarity with this. Analyze this and test all this and show that it all works, as well as build a circuit on here. And so, not the extender. This is the circuit schematic. They don't have to diagnose or analyze all this, but there's a number of things going on in here, including bouncing and debouncing switches. We'll talk about that in here. The mechanical bounce of a toggle or a push button, actual physical bouncing. It's imperceivable to you when you're pushing or flipping a switch, but it does actually bounce. And the time it does, you're like bounce, 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 bounce. When you think it just clicks once, every one of those bounces is coming on and off contact. And so you're getting more than one transition, more than one spike at a time. And the way digital circuits work is all the transitions, all the change of states, all of the most digital operations are on the clock edge. So if you have a bouncing switch, you're very likely creating multiple events where you intended to have one. So we'll learn about debouncing. And again, there's a lot of stuff in here. The students, if they don't have analog circuits, they don't want to analyze all this stuff here. But there should be, and here's actually a debouncing circuit with feedback. But so students will look at that and write up a little bit about this. One thing they may or may not do is, I have some old computers around here. I may ask them in the next lab, and I have done this in the past, to pull out the power supply and then try to use that as an alternative power supply. The circuit trainer has its own power, and our PLCs and other devices have their own power often. But you want to trigger something bigger, like a giant motor or something with a relay, or just maybe something 12 volts like a fan. This happens inside the computer. Inside the computer, you have 3.5 and 5 volts for your CMOS or TTL chips, but you also have 12 volts to turn your fans, to turn your drives, drive motors, and you need more voltage for better power. Power equals voltage times current. So if you get the voltage up, you don't need as much current. You can't really source that much current when you're going through chips. So the power supplies has 12 volts, and so we want to maybe have 12 volt motors that are tripped, like fans going on, and you can control that with a digital circuit. We may be doing that in the next lab. But to do that, we found when we first did this, it used to, in my olden days, I bought my first PC in 1983. I think it was a compact, the first clone of the IBM PC. It was like size of a sewing machine, like a suitcase. It's a better description. And it was, I'll go on the history of that, but I think I paid $2,000, which is the equivalent of like $6,000 nowadays. It had a 12 megahertz processor, a 10 meg hard drive, which was actually an extra $1,000, 10 meg hard drive. Because everything was just on a floppy. The operating system was just on a little floppy disk. And it was, but anyway, then you could just pull out the power supply and use them. But now we have these new power supplies, which linear switch mode. And so we had to order these 10 ohm, 10 watt resistors between each the voltage and ground, or it wouldn't work. So we might be doing this where we pull the power supplies apart, pull the computers apart, salvage the power supply, hook it up to another circuit, a controller that, hook them up to relays, driving fans, and then a controller doing something else. So that's the summary of that. And I guess I can show you what course this is in right now. We'll go in here. I'm going to hit F11 here. let's go back to in here. So again, in my computer engineering world here, you'll see all these manuals and you'll see projects of the past. This course now I'm in is 330, so you don't see it here because there's all these 332s and 3433s, but it was this course is in it by intensely combining two previous courses. So the course the students in right now is called Digital and Embedded Systems, and it's a mix of what was Digital Design 2, assembly language and interfacing with all this stuff, and also 332, which was pure digital design that they're doing now, and intro to assembly language, but all the combination of sequential design. And now it's all stuffed into one course, hopefully not too painful, with lots of links to things. So this is what we're doing in here. We're just in the beginning of the course here. And so I'm going to put a video, maybe on YouTube, but at least an MP4 on the web server here. And it'll be what we're looking at right here is this thing we've been looking at. Yeah. And then the students will be able, they've been doing simulation already, just combinational circuits, but then now they can breadboard something and understand. And in the process, we're also going to talk about floating pins and fan out. I thought that was in here. Let me see. Did I skip on something? I think I might have skipped over. There's tips down here, and this is what we should point out. Where are those tips? Should be down in here. Oh, yeah, right here. Yeah. So this is not the manual. I mean, this is our own custom manual, and these are things here we've inserted. This manual should be read thoroughly before engaging in any experimentation. As a general rule, never construct a circuit or insert any wiring with the pad unit on, you know, turn everything off first. Double check your wiring, then apply the power. Turn everything off immediately. Capacitors can actually blow up. We've had that happen once. Before placing a fuse, be sure the power switch is off. More stuff. Power supply, functional. There were some other warnings we had here. Yeah, familiarize yourself with the clock generator. Thought I had a couple other warnings on here and stuff, but might update this, although the video is what it is now. So floating pins. Oh, here we go. Never construct circuitry or wire or an interface with the PLCs or the FPGAs with the circuit trainer powder on. Yeah. Construct first, double check, apply power third. If something goes wrong, shut everything off. Talk to me. Make sure that the grounds are tied together. This actually caused a problem, but in general, you want to tie your grounds together. Be aware of potential fan out issues. So I have to describe that. Fan out means you can only drive so many chips with one given chip. You only can source so much current out of an output pin, and your digital logic that you think you're getting out of an output of a pin, you know, if it's a 1, it corresponds to a certain voltage that can degrade down to a lower voltage if your fan out is too much, where it's no longer a valid logic 1 anymore, because it's actually an analog value that's used, you know, somewhere between 0 and 5. We have thresholds at like 3.5-ish, above the 5 volts is a 1, logic 1. So you got to worry about that kind of thing. We'll also talk about floating pins. You can't just leave things not tied down. I didn't write it in here, but maybe, I have a separate thing on that. So yeah, you don't want to leave your pins not tied to something that doesn't mean logic 0, because it can pick up as an antenna. Bipolar transistors can act spuriously as an antenna and pick up a signal. If it's not tied to anything, it's not 0. You have to actually ground it and sync the current if you want a logic 0. Yeah, and then all this here is steps of, and I've got to make sure this is doable. We have several computers of different ages, and But anyway, I don't want to make this too specific to this one course because I want to use this video for other things. Okay, so I'll stop sharing here. And that is good for this video. Stop recording.